So I'm going to talk about Bluetooth Low Energy 5 PRNG today for fun and jamming and maybe more. So for those who don't know me, I am a security evangelist and also a senior security researcher at Digital Security, a French IT security company specialized in the IoT. And I'm also the main developer of BtleJack or BtleJack, which is a BLE Swiss Army knife. So we are going to talk about BLE5 and especially what's new in BLE5 specifications. And we will go through some specific features and also some interesting stuff in this protocol. So first of all, I'm going to recap what BLE is for those who are not familiar with this protocol. So this protocol has been introduced in 2010 as a Bluetooth Smart. So this is the first name of this protocol in Bluetooth Core Specification version 4.0. And it has evolved since then, version 4.1 in 2013, 4.2 in 2014, version 5 in 2016, and last version 5.1 this year, at the beginning of this year. So it's evolving very quickly as a protocol, and it's designed to be very effective. So people behind this protocol produce a lot of different versions, but the industry, it's difficult for the industry to keep up with this evolution. This protocol provides some security mechanisms, such as pairing, so you can exchange keys between two devices to be able to encrypt communications. And this pairing mechanism can be done with a PIN code. So this is something very easy. You just exchange a 6-digit PIN code between two devices, and you derive some keys from this. Also from out-of-band data, and also some elliptic curve Diffie-Hellman negotiation. So this is something provided by this protocol, and it's cool. Some version of this pairing are not very secure, as it was demonstrated before, years before. But some of them are pretty strong, such as the elliptic curves. This protocol also provides secure connections, so that means you can secure connection between two devices. And this is very interesting because this secure connection, BLE secure connection, is pretty strong when it's correctly implemented in the applications. And this secure connection provides encryption and authentication. That means nobody can tap into an existing connection or even inject some malicious packets in this specific connections. And last but not least, there is also what we call the channel selection algorithm. So to make things clear, this Bluetooth Low Energy protocol uses channel hopping to ensure to make these connections reliable. This channel hopping mechanism is very simple. When two devices create a connection, they're going to jump from one channel to another in order to avoid packet collisions. So this allows the connection to be steady, even if there are a lot of devices in the same room. And this channel selection algorithm is not a security mechanism, but when it comes to sniffing, when you are trying to sniff a BLE connection, this can be an issue because you need to know what this algorithm is and how to recover this hopping sequence in order to follow an existing connection. So this makes sniffing complicated. There are also well-known attacks, especially on BLE4, which is the first one, sniffing. You can easily sniff BLE connections, so this is pretty straightforward. Even secure BLE connection when the pairing is not so secure. You can also jam an existing connection. This is what I showed last year at DEFCON with BtleJack. So it's possible to disconnect two devices, and once the device is disconnected, then it advertises again, and you can connect to it and take control of it. But you can also hijack a connection. That means you can force a disconnection from one device to another and then exploit this connection without the other device noticing the disconnection. So it's possible to take complete control over a device this way. So again, you can do this with a lot of different various hardware. So on the left of the screen, there is the Bluetooth, which is a well-known device used to sniff BLE connections. In the middle, the Adafruit Bluefriend LA sniffer, which is one of the first Bluetooth low energy sniffer available on the market. It costs around $40. And on the right of the screen, there is the Microbit, which is a British broadcasting company sponsored board developed or designed to teach UK students how to code. And BtleJack uses this last board, this Microbit, to allow attackers to sniff, jam, and hijack some connections. Let's go back to the new features introduced in BLE5. BLE5 introduces a better throughput up to 2 megabits per second, a better range up to 800 feet or 240 meters, and an improved coexistence. I will go very shortly for these, the first two, better throughput, a better range. Basically, it adds two new PHYs to the Bluetooth Low Energy protocol. The 2 megabit per second uncoded PHY that doubles the speed of any BLE connection, so you can send more data in the same amount of time. And also the AD coded PHY, which improves the range 4 times the actual range for BLE4, but at 125 kilobit per second speed, and 2 times the same range at 500 kilobit per second. So this is some kind of trade-off you will do between range and speed. If you have a look at the packets sent over these two new PHYs, there is the AD coded PHY, which is a new PHY introduced in BLE5, and there is another PHY, the AD uncoded PHY, which is the actual, the BLE4 PHY. And in these packets, you will find an access address, which is a 32-bit value identifying a connection between two devices. But the problem is that the hardware we're using, such as the Microbit or even the Adafruit Bluefriend AD sniffer, this hardware cannot cope with these new PHYs. And that's pretty much the issue here. So our hardware may be useful, but for these new PHYs, this can be a problem. So we're going to cover this later. The main point here is that the BLE5 protocol introduces a new channel selection algorithm. So the old one is mentioned here. This is a very simple sequence generator based on some modulo. And the new channel selection algorithm introduces a PRNG-based random generator, PRNG-based channel selection algorithm. So this is based on a random number generator. This is a problem for us because, as Mike Ryan showed in 2013, it was very easy to recover a key value of the first channel selection algorithm, which is the op-inc value mentioned in this slide. But with the PRNG, the task is much harder because you need to break this random number generator to be able to sniff, hijack, and jam an existing connection. Luckily, the devices implementing this channel selection algorithm advertise a very specific bit, and if this bit is set, the CHCL bit, then this device supports this new channel selection algorithm. So basically, what are the consequences regarding known attacks on BLE5? First of all, there is a completely different new hopping pattern used. So basically, the old version, the first channel selection algorithm, generates a 37 channel sequence, and this new channel selection algorithm generates a 65,536 channel sequence. And basically, the device will loop over this sequence. So this is more complicated, and our first approach we got when we were developing the BLE4 tools could not work here. So sniffing new connection is still possible because you only need some software able to follow this new channel selection algorithm. Because at the beginning of a connection, you get everything you need to synchronize with this connection and follow packets. But as an attacker, we won't be able to jam or hijack BtleJack devices because the connection is already established, and we don't have these values used to compute the sequence of channels. We need to go to synchronize and follow a connection. So we also need a new hardware that supports BtleJack new files, but that's another question. It's just like some guys at BTSig decided to introduce this PRNG in order to mess up with the actual tools. Well, this is what I believed when I started this research. So let's see. Let's have a look at the random number generator. First of all, it uses a channel identifier value, some kind of value as a seed, which is a 16-bit value. This random number generator relies on basic operations, some add, multiply, XOR, bit permutation, and so on. And it also uses some channel remapping, but this was the same with BLE4. This channel identifier value is computed from access address. So this is the 32-bit value identifying a link between two devices, so basically identifying a connection. And the computation is the following. You take the access address bit 0 to 15, and you XOR this value, 16-bit value, with the access address bit 16 to 31. So you get a 16-bit value. And then we are going to use a lot of computation and a specific routine called MAM for multiply, add, mod. And basically this routine performs some computations and takes two values, A and B, 16-bit values, and produces a 16-bit output. And this is used 3 times in a row with some other computations in between to create a random number. Based on this random number, then we compute the actual channel for a given counter, a given value of the counter used here. So when this channel selection algorithm generates a sequence, it goes from a counter from 0 to 4K, and then generates every possible channel. And this creates a sequence of channels, and the devices will loop over this sequence. So when I saw this, I was like, whoa, what's this stuff? What the fuck? And I wasn't alone. I found some people on Twitter also complaining about this specification, and especially this PRNG. Well, maybe there's something to do. If you have a look at this generator, then you may have noticed that the channel identifier, which is a 16-bit value, is computed from the access address, which is basically public. So we need this through a sniffing connection. So this is a non-value. And also, the next value is generated from a counter, next random value, generated from a counter. So not from some kind of internal state that usually PRNG is used to create another random value. So since access address is public, then we can go from 32 unknown bits to 16 unknown bits. So this is quite easy. And this PRNG, well, is it really a PRNG? If you look at the specification, then we know that the channel identifier is constant since it's derived from the access address. And what this function does is that it generates a fixed sequence of 65,000-ish values indexed by a counter. Normally, these counter-based random number generators are used to parallelize. Sorry, in French. This is a very easy excuse, but anyway. Yeah. So this generates a fixed sequence of values, and then this is very interesting for us for leading the attack. But what that function does, in fact, just randomize some kind of channels, and that's it. So what do we need to break it? If we consider the channel, just consider the channel identifier as known, since it's derived from the access address. We are left with a 16-bit unknown value, which is a counter. And if we can figure out where we are in the sequence of this 65,566 values, then we would find out what this counter value is. And once we get this value, it's done. You can synchronize with a connection and then follow a connection and then jam, hijack, and do whatever you want. So, how to get the counter value? As an attacker, we can only monitor some events. And these events are the following. We can determine when the packet is received on a specific channel. And based on this, you can also determine when the time between two packets received on two different channels. So basically, we can deduce something from some measures we can do on this on a specific connection. If all 37 data channels are used, then the channel selection algorithm uses a very simple equation or simple computation to derive the channel for a specific counter. But if not, if these channels are not all used, then this is more complex. But in fact, this it doesn't make things more complicated in this way. But I will focus on the first case. The first case is that we are going to use all the 37 data channels to make things simpler. My first approach was to use a sieve. I'm quite sure you know about Ewasothen's sieve used to find prime numbers. We are basically doing the same. Our goal is to eliminate every possible candidate in multiple rounds and in the smallest number of rounds, to be more precise. The prerequisites here to do this is to be able to know the hop interval value, which is basically the time between two hops in the hopping mechanism. So, how it works? We are going to consider a counter of 0. So, just say that it's 0. It's hypothetical. It's not the real value we are looking for. And we compute channel C0 from this PRNG function with this candidate counter and based on the channel identifier, of course. And we wait for a valid packet. So, we got a packet at time T0 on channel 0. On channel C0. And we do the same on the next channel. So we increase the counter with a counter of 1. We compute the next channel, and then we wait for a valid packet, and we got a packet at time T1. So then we measure the time spent in between. So delta T equals T1 minus T0. And since we know the hop interval, the time between two hops, then we can deduce the number of hops between these two packets. So by doing this, we can create a pattern that will be very useful to sieve the sequence. So basically, we're just going through the sequence and looking for a specific pattern composed of two channels. Channel C0 at, say, index 200, for instance, and at index 200 plus n, channel C1. By doing this, you will get between 200 and 400 candidate values for this counter. So remember, we are looking for the counter used at T0. And we do it, we repeat the operations. We take the first candidate out of the remaining candidates, and we compute C0, C1. We wait a packet on channel C0, then C1. We deduce the number of hops, and then we apply our sieve again. We are going to filter all these candidates and keep only the matching ones. And you do this until one candidate left. And this candidate is the value of the counter at T0. So, since I had no BtleJack devices at this time, I decided to implement, to simulate this attack. So, I will show you the result of this simulation. So I wrote everything in Python 3, and I create this script, CSA to simulate pi. So basically, at the start, there is a counter randomly generated, which is 13,600, and I will go through every candidate, each round, reducing the number of candidates. So it's here 21, 11, 6, 3, 2, until we get a single candidate. And this candidate is 13600, which is in fact the value we are looking for T0. So that's good. Yeah, I love when a plan comes together. The problem here is that we need to know what this hop interval value is. I suppose this value was known during my first simulation, but in fact I don't know this value. So how to guess this value? Well, it's some basic math you have to do. Since we are going to measure time differences between packets received on various channels, then we can we can compute the GCD, the greatest common divisor of all these measures. And since these times are normally multiples of the value we are looking for, we will get this value. So again, I simulated this computation. Well, it's very quick, so I have no video for this one. But by doing only 10 measures, I was able to recover the hop interval. And I performed a lot of tests, and this test showed that if you perform only 5 measures, if you compute 5 measures, then you get an approximative success rate of 95% of success. So this is pretty good. If you get 10 measures, then you are quite sure to get the correct value. But that's cool. So basically, what I got here is that a way to recover the hop interval value, and another way to get the counter value, the value of the counter, sorry, at a specific time. So let's do it in practice with a real device. There is a problem, in fact, is that this version of the protocol has been released in 2016, and still there is no compatible devices in the market. So I wasn't able to find something to buy that implements this protocol. So I'm sorry, there is no video of a sex toy hack this time or a drone hack. But anyway. So, based on my first research, I decided to try to apply this attacks on some BtleJack devices. So, since there are no BtleJack devices, I'm going to make some. I ordered on a site, on a website on the internet, 2 development boards from Nordic, which support this new protocol with the correct SDK and the correct stack. And I just programmed this boards with very basic examples. One making a LED blink and providing a BtleJack compatible device, and another able to connect to the first one. So basically 2 devices that can create a connection in between and transfer data. And I also decided to improve my BtleJack tool by implementing some features, new features for BtleJack. So BtleJack can do the job, but only for the legacy file, which is the 1 megabit per second encoded file. But doesn't matter, my development boards are compatible with this file, so it's okay. And I modified BtleJack to compute this hop interval while this tool was mapping channels, because usually when you're attacking an existing BLE connection, you need to know what channels are in use. You remember, I suppose that all 37 channels are used, but this is not always the case. So by doing this, I modified the code to be able to get this hop interval while mapping. But I faced a first problem. This problem is that normally when you are using CSA #1, the first channel selection algorithm, this is a 37 channel sequence, and you loop over this sequence. But there is no doubles. You know, each channel only appears once in this sequence, so it's very easy to determine this hop interval value. And you measure a time spent between 2 packets received on the same channel, and then you divide it by 37, and it gives you the value you want. But this is not the case with this random number generator, since a channel can appear twice or maybe more during the sequence. So I had to compute automatically a timeout to be sure that a channel is correctly used. Anyway, and I tested this GCD-based technique for recovering the hop interval, and it works pretty well. In fact, once you smash, once you solve all the issues based on timeout. So this is an example output of what I get when I try this hop interval recovery system on this connection. So I got a hop interval of 160, which is pretty much it. So that's good. Great success for the first time. But the main part is to be able to recover the counter used at a specific time during the connection. So I implemented this algorithm, the sieve algorithm, and I started trying this algorithm. So the first run went pretty well. I went from 65,000 candidates to about 250 candidates, which is what I showed you a few minutes ago. So that was pretty cool. But the next round completely messed up. I wasn't able to get any data. So I was a bit puzzled. And it turns out that my filter routine took a hell of a time to execute. And it induces a delay, and I get lost in the connection. So this is a simple algorithm problem. So yeah, I was a bit pissed at this time. So I decided to redesign my attack, and to solve this problem I moved from a sieve to a pattern machine algorithm, which is basically what I was also using. So normally during my sieve attack I measure and then I filter all the candidates. This time I'm going to do all the measures during the first part of the attack, and then filter all the candidates just at the end. And by doing this I get a more complex pattern, but in fact I'm quite sure to get the correct value. And by doing this you end up with 10 delta t values, so some times difference between packets received in various channels. And based on this we look for this hopping pattern in our sequence, and we deduce a counter exactly as we did before. And yeah, that worked. I was able to guess the counter value. So I will show you an example of this later. So that was pretty cool. So from this, I told myself, yeah, that's good. You get the hop interval, you get the counter value. Now this is easy peasy. Everything you need to do is just to synchronize with the existing connection. Well, good. So I developed the firmware in order to synchronize with the connection, and yeah, there was some kind of issue here. Didn't work at all. So I got the correct hop interval value, I got the correct counter, but I wasn't able to synchronize. And I looked at my code a bit once more, just to be sure that I didn't fuck it up. And I stumbled upon this part of the code. So this is the filtering routine. What this code does is just going through all the candidates and filter this candidate. So this is the second version of the approach. So I need to go through the 65,000 and 536 candidates, and it takes a hell of time again. And by doing this, I was just 13 hops away of the correct value at the moment I was trying to synchronize. So by doing this, just adding 13 to the counter value, I was able to synchronize to an existing connection. And that's pretty much it for this recovery. But I will show you now a video of everything working with this firmware. So for the video purpose of the video, I just provide the channel map and the hop interval value. So as you can see, this tool is trying to recover the PRNG internal counter, which is an unknown value, 16-bit. It takes some time, generally less than a minute to deduce this value. So it's pretty cool because if you are trying to attack a real life device, you have to be near to the device to attack it. So if it takes less than a minute, it's okay. Should be very short. And once the counter has been recovered, then we capture data sent over these devices. So by doing this, we got the correct value for the hop interval, and then we get the correct value for the counter. So that's pretty much it. You get a way to sniff. You get a way to sniff data over a BtleJack connection. But remember, it's only on the 1 megabit per second encoded file. And you can also try to jam a connection. So basically, once you are synchronized with this connection, you can inject packets as well. And this is what I did last year when I was attacking some devices. And this can also be done with my BtleJack devices. Well, it's how to say? This is something very special because I got my device on the screen here, so I'm going to recover the PRNG internal counter. And you can see some LEDs normally at the bottom right of the screen. This LED, when it's LED 2 that is lit, then it means the connection is still active. I'm going to jam this connection and pay attention. This will be very quick. There is some LED blinking, telling us that the connection has been lost and disconnected. So here I successfully jammed an existing connection, BtleJack connection, by using BtleJack. Yep. Back to the slides. So, since everything went smooth with this attack, I decided to release a new version of this tool, of BtleJack, version 2, including all this research I made on this channel selection algorithm number 2. So it's working, but I tested it on a very few devices. I only got 2 of them, so I don't know if this tool will work with any type of devices, BtleJack compatible devices. So. I give you the code, I give you all the tools. This version of the software has not been published on pip, just not to mess with the actual version, because I'm not sure, since I made a lot of modifications in the firmware, I'm not sure that this version may alter the behavior of the actual BtleJack version. So just to make things clear, you can clone this repository and then install the device by using some Python AutoMagic installer, Python setup py, and that's it. So all the code is available, open source as usual. So to conclude, not so quickly, but anyway, what this talk demonstrates is that the BtleJack CSA number 2, so the second channel selection algorithm, PRNG, is weak. But there is a reason for that. I remember at the beginning of this research, I was just thinking that this PRNG has been introduced in this version of BLE to piss hackers trying to attack BLE devices. But in fact, I thought I had some other thought about this PRNG, but well, it's not really a PRNG as it's used here. And of course, 16 bits out of 32 can be easily guessed, and the last 16 bit is a counter, so this is very easy to recover. But in fact, this PRNG has been designed to improve coexistence, not security. The goal of the guys who designed this protocol, this channel selection algorithm and this PRNG in particular, was to improve the coexistence of devices in the same space. By doing this, yeah, it works. You can get a lot of BtleJack devices, and with this system, you can get a lot more devices that we are used to have in with the BtleJack version. And also, the counter-based random number generators are easier to implement and consumes far less power and memory. So in the IoT world, this is something that makes sense. So is it a vulnerability? Well, I don't think so. I don't think it's a vulnerability, but in fact, it doesn't stop hackers to jam or hijack existing connections. Future work will include a lot of development for BtleJack. As I said, there are 2 new files introduced in this BtleJack version, BtleJack protocol, and these new files are supported by a new Nordic system on chip called the NRF 52840. And this chip is very interesting because it implements all the files natively, so we don't have to do some SDR stuff or anything. We can just use the features of this chip to be able to decode and anchor the data packet over the air. So this is quite interesting. But the fact is that it demands a lot of work to port BtleJack to this new platform, because both of them are made by Nordic, but there are some differences in the way these chips handles the BtleJack protocol. But luckily, someone called Marcus Mengs made some research recently on Logitech unifying devices, and this dude made a lot of code compatible with this chip. And I talked with him. We exchanged a lot of mails. And this guy has some piece of code ready to use to implement this. So I think if he's kind enough to share with me some tricks he did on this chip, I will be able to port BtleJack to this new platform and get rid of the microbit stuff. So this is it. I think I said almost everything I wanted to say. The resource materials, all the notes, scripts I wrote, everything I showed you with the Python scripts is also available on the GitHub repository, which is the following: BtleJack-research on GitHub. So you can get everything I developed and try it. Insult me if the code is dirty and not that clear. But in fact, you can simulate everything the way I did and test it against some, I don't know, maybe some new attacks you're looking for. So thank you very much for attending this talk, and I hope it was, cool.